Today we will look at H, P, and the HP versions of FEM. So we saw H version of FEM. Basically, you improve the approximation by reducing the mesh size. We saw the P version of FEM. You improve the approximation by keeping the mesh fixed, but then you increase the polynomial interpolation order. And there is also the HP extension, which, as you may guess already, does what? HP? Both. Okay. And this is good because it's going to allow us to try to understand and classify problems in FEM. There are some problems that are nice, other problems that are not so nice, and then there are the nasty problems, okay? And then we're going to get into the theory that will help us understand how these problems are going to converge, right? How our method is going to converge for these different problems. So, well, we started with H version of FEM. And normally, what you will see is that we use either linear or quadratic approximations at most. And this is what you have in every finite element software out there. So peak is equal to either 1 or 2. And then the idea is, well, you improve the approximation as you reduce the mesh size, right? Where H is now the size of the largest element. So why the largest element? Well, because it's the largest element, the one that is going to control the accuracy, right? If we know that the approximation gets better with smaller h, then obviously the largest h is going to be the weakest link in the approximation and is going to be the one determining the accuracy. We saw the P version of FEM, where, as you remember, the idea was to keep the mesh fixed. And then the approximation is improved by increasing the polynomial interpolation order. With a caveat, right? We said, well, not every basis is actually a good basis for the p-FEM. And we saw that if we use like Legendre polynomials that are orthogonal, that is a better basis than the monomials. So here, P would be what? The smallest or the largest polynomial order? The smallest. Okay, well, we're going to look at a couple of examples of problems. The first one is a problem with a smooth solution. And well, for this, I have a, let's say, a bar. Again, we're going to be always looking at the bars. And then we are going to have some sort of like, remember, this is the load per unit length. And it's basically b of x is equal to a trigonometric function, so minus sine of 8x. Well, the exact solution for this problem, which is very easy to get, right? Because you have a second order differential equation. You have the b function, which is a sine. So you just integrate twice, apply boundary conditions. Here the boundary conditions are what? 0 displacement at the end and 0 traction, 0 axial force at the other end, right? So u of x is going to be equal to 1 minus, minus 1 over 64 sine of 8 of x plus 1 over 8 cosine of 8 times x. Okay, well, I have these problems in Mathematica just to plot them how they look like. And so this is basically one of them. This is the way the solution looks like. And this is where we close our door. Okay. So the solution looks like this, and you can see it's very smooth, right? Very nice. Very, very, very nice. And well, you would expect h-FEM to do very well, right? At least on problems that are smooth, you would expect that the functions, linear quadratic approximations, are going to do well. So if this is the log of E being some sort of error, again, we look at energy norm of the error, as we saw multiple times. And this is log of n being the number of degrees of freedom of the problem. Well, here, maybe I'm going to choose this guy here. This is going to be h-FEM, but this is going to be p-FEM. Okay? And we say that h-FEM gives the so-called algebraic rate of convergence. In other words, the rate of convergence is constant. And that, of course, you can see from the image. Is a schematic, of course, but you see that there is a straight line. Well, the rate of convergence, which is actually the slope in log space, is actually is constant. It does not change, right? Whereas p-FEM gives the so-called exponential convergence. Rate of convergence increases. Yeah? Okay, well, this is a nice problem, okay? Let's take a look at a different problem. So problem 2. Problem with non-smooth solution, okay? And here, again, I'm gonna copy this. For this problem, b of x is going to be equal to lambda multiplied by lambda minus 1 to the power of multiplied by x to the power of lambda minus 2. Okay, where lambda is, well, let's put it here, lambda is a constant. The solution to this problem, the exact solution, is minus x to the minus lambda plus lambda times x. And so if we now look at the solution for this problem, nope, here, this is what you get for lambda equals 1/2. And so there is a point in the domain where the solution is actually singular, but one point, right? So it's not a nice solution. It's actually a solution that the finite element method has a really hard time trying to get an accurate solution for. So now, when we look at what happens with the convergence rate, well, for this problem, h-FEM remains algebraic, but now we have also p-FEM is also going to remain algebraic. Well, for this problem, there is actually a way to fix this issue. We could potentially have or devise a mesh where something like this. This is the first element. Where here we said, well, I want these elements to be p equals 1. Here I'm going to use p equals 2. And then this is going to be p equals 3. And here p equals 4. And then I'm going to basically, this is going to be 0, my coordinate 0, L, Q3. L is the total length. Then this is L, Q squared. LQ, and then L, where your Q is a geometric factor that, if you see, is basically pushing the nodes more closely together next to the singularity, right? And for which it has been found that an optimal value of that Q is more or less equal to square root of 2 minus 1 squared, which is approximately 0.17. And in practice, people use Q 0.1, 0.15 in that range. So these are the so-called geometric meshes, okay? And so, well, the locations here, X, is equal to 0, for J equal to 0, and L, Q to the number of elements minus J, for J equals 1, 2. These are basically the locations of the coordinates. Okay, this is so-called the HP extension, and the HP extensions, as you already know, is actually going to improve the approximation, and it allows you to recover again exponential rate of convergence. So HP And so for problems that have a singularity at a single point in the domain, for those problems, we recover the exponential rates. Now, this discussion helps us to classify the problems in 3 kinds. So now I'm going to talk about classification of boundary value problems based on regularity. Regularity means essentially how smooth the solution is, right? So the solution is sufficiently regular, that means it's sufficiently smooth, okay? And so there are problems in category A where U, the exact solution, is analytic in omega, right? That basically means that can be expanded indefinitely in Taylor series. There are problems in category B where U is analytic in omega, except in a finite number of sets of zero measure, and I will explain what this means in a second. Sets of zero measure. Well, as we saw right now, right, this problem, the singularity just happened at a point. And a point in a line, it is a set of zero measure. So basically, it's an entity that has no length. It's the same as a line in 2D. A line in 2D is also a set of zero measure. So what would be the equivalent set of zero measure in 3D? Yeah, well, a surface, right? A surface in 3D would be a set of zero measure in 3D. A line would also be a set of zero measure in 3D. A point as well. In 2D, a line and a point are sets of measure 0, right? In 1D, a point is a set of zero measure, right? So those are, so as long as you have these singularities happening at sets of zero measure, then the problems can be classified in this category B. And then finally are the nasty ones. Category C, and this is basically U is not in A nor B. Those are the ugly ones. Okay, so now that we have some classification and we understand that there are some different kinds of boundary value problems, let's see what theory predicts for each one of these problems. So, and then we get into the so-called a priori error estimates. And this is where we learn what is supposed to be the rates of convergence that we're going to get depending on the type of problem. So as we recall for a few seconds ago, algebraic rates algebraic estimates are often of the form, and now we're talking exclusively about algebraic estimates for both h-FEM and p-FEM. Remember that p-FEM had also an algebraic rate of convergence for problems that were not so smooth, right? For those in category B. So in here, h-FEM, U minus UH, which is your error in energy norm, measured in energy norm, is less than or equal to C1, which is a constant, multiplied by H, the mesh size, to the power of beta H, and beta H is the so-called convergence rate, multiplied by the norm of U, which is again your exact solution, the norm in the energy norm of the error on the left. So if you see, we can bring this guy here, right? And then we have some sort of relative error in energy norm, right? And so C1 here is a constant that is independent of U and H. H is the mesh size, as we know already. And then beta H is the so-called rate of convergence. And that is dependent on the polynomial interpolation that we use and the exact solution. And we will see in a minute how this looks like. Again, we're gonna use a log-log plots also in the project, right? So obviously, when we take this guy here and we define everything that we have in the left as some sort of relative error in energy norm, right? And then we take the log of those quantities. Well, so this guy here is going to be split into two, right? We're going to have the sum of the log of C1 plus beta H times the log of H, and that essentially is the equation of a line, and that is why you recover this so-called algebraic estimate. Okay, so let's take a look at p-FEM. For p-FEM, U minus UH, error in energy norm, is less than or equal to C2, which is again a constant multiplied by 1 divided by P to the power of beta P times the norm of U. And here again, C2 is a constant, P is the polynomial order, and beta P is my rate of convergence. Okay, notice how I use beta H for h-FEM, beta P for p-FEM, but they are both algebraic rates of convergence. Okay? All right, finally we get into the so-called exponential. These were algebraic rates. Now we're going to get exponential estimate. And the exponential estimate says that U minus UH measured in energy norm is less than or equal to Z divided by exp, so e to the power of gamma n theta. And here gamma and theta are constants, and n is the total number of doves. And notice how the moment that we're looking at exponential rates of convergence, obviously we're talking about p-FEM, right? So if we're gonna look at a mesh that is fixed and we are increasing the polynomial interpolation order, well, it really doesn't make sense to say anything related to H anymore, right? So we have to use the total number of degrees of freedom, because for the same mesh discretization, you can have two elements, but of course you can increase the polynomial interpolation order, and that is going to increase the number of total degrees of freedom. Yeah? So let's see how they look like, each one of these estimates. So let me copy this. And we're going to start with our algebraic estimation.
I think there is a norm of U missing.
Normal?
Norm of U.
Sorry?
At the
Where?
end of the last formula you gave us.
Ah, yeah. Yeah, I'm missing that. Yeah, because again, eventually it's going to be a relative error. Thanks. Okay, so indeed, if we define U minus UH divided by U, everything in energy norm, as, say, E, that's the error, relative error, right? Well, if we take one, we get, let's take the log at each side plus beta H multiplied by the log of H. Maybe I move this a bit down. Yeah? So you get something that looks like this, where that is your rate of convergence, right? And keep in mind that here I have plotted basically the log of the error versus the log of h. And it makes sense because in h-FEM, we decrease the error by just basically reducing the size of the element, so it makes sense that we do it in terms of h. But we can also do it in terms of the number of total degrees of freedom, right? So let me just maybe copy this to the side. And if now I say, well, this is going to be instead n. Where is it? Then I don't get this anymore. I get something that looks like this. And now, of course, as I reduce the size of the elements, I'm also increasing the total number of degrees of freedom. Obviously, the algebraic rate of convergence is going to remain constant, right? So we don't get, I mean, expressing the same solution in different ways doesn't change the solution, obviously. And so now, of course, the slope is negative because we are expressing it in the terms of the degrees of freedom as opposed to h. But now the rate of convergence is, let me see here. Oops. I cannot draw a straight line. And this is going to be beta h divided by d, where d is the dimensionality of the problem. And this comes because h is more or less equal to 1 divided by the total number of degrees of freedom to 1 divided by d, and then d is the dimensionality of the problem. And you will see that, for instance, if you're solving a problem with linear elements, and whereas in this plot you get a convergence rate of 1 in energy norm, right? Well, if that problem is in 1D, you will also get a rate of 1 here. But if it is in 2D, that gets half of the rate. And that is normally what we see in smooth problems, okay? When you get optimal convergence, you see that depending on how you express, you get a different value for the convergence rate, but that is because the dimensionality of the problem has to be taken into consideration. And keep in mind that here we are only looking at quasi-uniform meshes.
Does D change, for example, for a 1D bar,
Yeah.
if the elements become quadratic or not the same?
Yeah, of course. So you will see in a minute, we're going to make a nice table where we're going to see how these convergence rates are supposed to behave. But, well, for linear problems, you get a rate of 1. For quadratic, you get a rate of 2 in h, right? Log of h versus log of the relative error. And cubic 3, quartic 4, and so on. If we are expressing the error in a different norm, like for instance the L2 norm of the error, then our rates are going to be higher. So for instance, for linear elements, the convergence rate in L2 norm is not 1 but 2, right? Because we're no longer looking at the derivatives anymore of the function, we're looking actually at the function itself, and that converges faster, okay? So it's important also at the norm of the error that you are using to do these computations. And let me finish here. Of course, if we make this change now, our equation of the line becomes minus beta h divided by d log of n, and that is here again the rate, and you see that it's negative, and so you expect obviously to have a different type of slope. Okay, this is for the h version of FEM. Okay, algebraic convergence. So we only look at reducing the error by just reducing the size of the element. So let's take now the second one, which, if you remember, was p-FEM, right? So we're going to basically look at this estimate, and we're going to do the same trick, right? So we take this guy, we put it here, we define everything on the left as our relative error in energy norm, right? And we apply the log to both sides, and then you will see that we get something that looks like this. So the log of E less than or equal to the log of C2 minus beta P log of P. So we have P here. This is going to be beta P. It looks like that. Yeah? And then, again, keep in mind that this is p-FEM, but algebraic convergence. And that it was in the problems that were not so smooth, right? The ones that have something going on in a set of measures 0. And finally, we have the exponential rate is less than or equal to log C minus gamma n theta log of E, and this is equal to 1. And if we take the log of this expression again, right, is equal less than or equal to minus log gamma minus theta log n, and this is the inequality only holds for constant C greater than or equal to 1. Then I can write it like that, and for that case I express my solution like this. Basically, let me get rid of that. Now here I am plotting not the log of E, but the log of E. So I apply the log twice, and then this guy here is theta, which is the other constant. Okay, so in other words, if you recall, for the exponential rate of convergence, we saw that the rate was increasing, right? We see it here, right? The rate is increasing. Well, but if you take the log again, right, you will see that that remains aligned, and that is how we can obtain the slope to be that theta constant. And so with all this information, now we understand what the theory is trying to tell us. So we're going to classify all these in the different categories. So we have category A, category B, and category C. And then we have H, we have P, and we have HP. Well, for category A, remember, smooth problems, nice problems. We get algebraic convergence. And as we said, beta H is going to be equal to P. Remember, this is energy norm. And so a linear approximation is going to have beta H equal to 1. A quadratic approximation is going to have beta H equals to 2. A cubic, beta H equals to 3. And remember, we always talk about error in energy norm, in this case for h-FEM, as a function of the log of H. If I move now to number of degrees of freedom, that changes, right? So I have to account for the dimensionality as we discussed. So if we are in 1D, the rates pretty much remain the same, but if we are in 2D, the rates are going to be halved divided by 2. If we are in 3D, divided by 3, okay? Again, in the log of the number of degrees of freedom, and then the log of the relative error in energy norm. Okay, for problems in category B, you get algebraic convergence for h-FEM, but now your beta H is going to be perhaps limited by the singularity of your problem. So it's going to be basically the minimum between P and K minus 1. And we will talk about what K is soon. Or P if you have an optimal mesh. You arrange your elements properly. So that K is the order of the Hilbert space where the exact solution lives, okay? It's basically what we call the regularity of the solution. So when the solution is very, very, very regular, very smooth, that K is very high. But if the solution has a singularity, that K is not so high, and so it may conflict here with the polynomial interpolation order, right? So problems in category C, which are the very nasty ones, we get algebraic convergence, and we can only state that beta H is greater than 0, which is okay, it's good. At least we know that they converge for those problems. Okay, for P, problems in category A, what type of convergence we have? Exponential. So we know that theta is greater than or equal to 1 over d. D is the dimensionality. For problems in category B, p-FEM gives algebraic. And now beta P is also going to be dominated perhaps by the regularity of the solution. This is for uniform meshes. And then for C also gives algebraic convergence. Beta P is greater than 0. And then the HP, we get exponential convergence. With theta greater than or equal to 1 over d, which is the same. We get exponential convergence with theta greater than or equal to 1 divided by 2d minus 1. And then finally, for C, we get algebraic convergence. Okay, just to complete the table, here D is the dimensionality of a problem. And then K is the order of the Hilbert space U lives on. As we said, the regularity. Okay, so for problems in A, U belongs to HK, where K is very, very, very large. But for B, we know that K is greater than or equal to 1. But you can see that it can control the convergence rate. And this is, for instance, what happens in fracture problems, right? Fracture, it has a singularity. You have a singularity at the crack tip. And so we know that it is controlled by the rate is controlled by the singularity. The solution is not so smooth, right? And so there is a set of 0 measure at the crack tip where our stress field goes to infinity. So we have some sort of 1 over the square root of R singularity. And so when you compute the rate, actually, if you don't do anything special, you get a rate that is controlled by this. Yeah?
Are you using Are you using singularity and that zero measure interchangeably?
No, you can have something. Singularity means something goes to infinity, right? A set of zero measure means, as we discussed, a point in a line is a set of zero measure, right? It doesn't have so measure. The word measure is used to describe let's say a dimension in 1D, right? An area in 2D or a volume in 3D. So if I look at three-dimensional problems, and I think about, okay, what is a set of zero measure in 3D? Well, obviously, the only thing that has measure in 3D is volume. So if I look at the surface, that has zero measure. If I look at the line, zero measure. A point is zero measure, okay? Let me check. Okay, 40 minutes. So we stop here, and then we meet in 15 minutes to continue with the last part of the lecture.